So the first question here, for this given function, they want you to find the gradient of the normal to the curve at this point, x equals e. So to start off, we're going to find the gradient of the curve before finding the gradient of the normal. So we need to find our derivative function. We're going to be using the product rule. 2x multiplied by ln x plus x squared times the derivative of ln x, which is 1 over x. You'll notice that the 1 over x and the x squared should cancel. So you'll be left with x. Then we can factor the x out to get x times 2 ln x plus 1 should be our derivative function. So first we're going to need to find the regular gradient of the curve. And gradient just means slope, by the way. So we're going to plug in e. So f prime of e is equal to e multiplied by 2 times ln e plus 1. And the value of this, if we evaluate it, so ln of e is just 1. So this inside is 2 times 1 plus 1, which is 3. So this is e times 3, which is 3e. And since the question asks for the normal at this point, we're instead going to have to use the negative reciprocal, because in order to find the reciprocal of something, you take 1 over that number and make it negative. So 1 over 3e and make it negative. And that's your solution for the first question. If the gradient of the tangent to the curve of f at x equals a is 5a, find the value of a. What this means is that we have, if we plug in into our gradient function, a as our value, and then the result should be equal to 5a. So we're going to use this equality. If we remember here, we should be plugging in, for every instance of x, our function was x times 2 ln x plus 1. So a times 2 ln a plus 1. And we know that this should be equal to 5a. And now we can begin solving. So let's divide both sides by a. Let's subtract both sides by 1. So we'll get 2 ln a is equal to 4. Divide both sides by 2. So now we have a logarithmic expression. This just means e to the power of some number would give you a. So e to the power of 2 would give you a. So a is e squared. So the second question here, you might find some use in having some pattern recognition. So they're asking for the first derivative, second, and up to the fourth derivative. So the first derivative, let's just take the derivative of this function. It's going to be negative, and the derivative of sine is going to be cosine, and we can't forget to chain the inside, so we'll get negative cosine of 2x times 2. Let's rewrite that. 2 cosine 2x. So f prime prime of x, if you remember, the derivative of cosine is going to be negative sine, so this entire value will become positive. We'll have to multiply by 2 for the inside again, so we'll get 4 sine 2x is our answer for that. And for the third derivative, they don't use prime prime prime, unfortunately. It's going to be a positive value, as sine does not go negative. So we'll have to multiply by 2 again. 8 cosine 2x. And for the fourth derivative of cosine, going to make it negative 16 sine 2x. So I'm going to go another step further and take the fifth and sixth derivatives just for the next question, because I already know what it is. So this is going to be negative 32 cosine 2x, and the sixth derivative is going to be positive 64 sine 2x. And I'm sure you can see how I get the pattern. So there appears to be gaps of 2 where it's positive, then gaps of 2 where it's negative, and it repeats. And this is a power of 2, which is really important because the next question asks you to find a general form for the 2nth derivative of f of x. So you can interpret the coefficient at the front as a power of 2. But since they're asking for the second derivative, if we look at every other derivative, that would be the second, the fourth, since n is going to be an integer. The second derivative, it's a multiple of 4. And the fourth derivative, it's a multiple of 4. So rather than having a power of 2 to the power of 2n, like this, we can just write this as 4 to the n. So we know that this expression is going to have a 4 to the n term, but it's a series, right? A geometric series, if you remember. A times r to the n minus 1. So a is our first term, r is our ratio, and n is the number at which we're increasing by. So our first term in terms of the coefficient for this function is 4. So we'll have 4 times r, which is also 4. Oh, sorry. Yep. And then our n is going to be n minus 1. So this is 4 to the 1 times 4n minus 1. This is just equal to adding the exponents, 4 to the n, and that's the reason why we have that number. But in order to alternate the positive and negative sign, we're going to need to have some kind of rule to include these values, since 4 to the n will only result in positive numbers. So it's probably going to be negative 4 to the n. Let's check that. When you have negative 4 to the second derivative, which means that our derivative, our n is 1, then we're going to have a positive value, which means that we actually need a negative outside here, because this will alternate every value you get. So when n is 2, which means we're taking the fourth derivative, when n is 2, then we'll have 16 inside, and then the value will turn negative, which gives us the correct coefficient. Yep. So that's the coefficient done. So f to the 2n is going to be equal to negative 4 to the n. Then of course we're going to have to multiply by one of these terms. And we'll notice that every other derivative is using a sine term. So we can just write sine 2x. And that's going to be the answer for this question. For the third question, we're given a function and it's graphed for us from negative 4 to 7, and we're given the information of a local minimum, which we need the we know the location of, and the local maximum is at a point B, which we don't know, so we'll have to find that out later. But for now, it tells us to use the quotient rule to show that f prime of x is equal to all that. So let's copy our function down here. So negative 2x divided by x squared minus 5x plus 4 is our function. So to derive this with the quotient rule, if we remember, we're going to have to take this top part as f and this part as g. So f prime. Oh, and we can pull the negative to the end. Because you can have negative d dx. Because you can multiply by the coefficient at the very end rather than right now. So we'll have negative, and then this will be f prime. So let's see, we'll have negative times the derivative of 2x is just 2 multiplied by the entire bottom part. Subtract 2x multiplied by the derivative of the bottom part, which is going to be 2x minus 5. All divided by the entire bottom part squared. And if you look at it, it's already kind of resembling the form they want us to show. So up here, we can expand this in. We'll get this is equal to 2x squared minus 10x plus 8 minus 4x squared plus 10x. And if we cancel some terms out, we'll get negative 2x squared. These 10x and 10x terms cancel, plus 8. And from there we can factor out negative 2. I think that's when they want us to do. Yes, they want us to factor out -2. So we'll get -2 times x squared minus 4. And yeah, that resembles this form. And this negative will cancel with the negative later. So we'll have 2 times x squared minus 4 divided by x squared minus 5x plus 4 squared, which is something they didn't want us to expand for obvious reasons. And yeah, you can write q, e, d. So with this derivative function now, they're asking us to find the coordinates of b, which, if you recall, is our local maximum. It looks to be somewhere around here, but we can't know for sure yet. So let's try and find that. So the local maximum would be a point where the derivative is 0. So this is our local minimum a, as you can tell, because it dips down. And there's a point where the slope is 0, which means at some point our derivative function is set to 0 to find the point b. So f prime of x is going to be equal to 2 times x squared minus 4 over x squared minus 5x plus 4 squared, which was going to be equal to 0. We know that the numerator must be equal to 0 for the entire fraction to be equal to 0, and it doesn't matter what the denominator is. So we're going to have 2 times x squared minus 4 is equal to 0. You can divide both sides by 2. We can move the 4 over. X squared is equal to positive 4. But when we take the square root of both sides, then x can be plus or minus 2. So it's important that we get plus or minus because with a bit of logic and without using the second derivative, we can figure out which one is the local minimum and local maximum. Because we have two values, -2 and 2, which tell us that we have one local minimum and one local maximum according to the graph. And obviously, they give us that the local minimum is at positive 2. And clearly you can see, even if they didn't give you this x value, you can see that this is further along to the right. This local minimum is further along to the right, which means it's a positive value. And the local maximum looks to be somewhere around here, b. So the x coordinate of the local maximum, b, is going to be -2. And you can find the y by plugging it back into the original function here, up here, if you really wish, but I'm not going to. And finally, given that the line y equals k, so it's a linear line, y equals mx plus b, does not meet the graph of f, find the possible values of k. Or sorry, y equals k would imply that it is a horizontal line. So y equals constant, which means it has no slope, but it's just any horizontal line that can be fit into this graph. If we look at this graph, we can see that these are the values that would be permitted in between this gap from the local minimum and the local maximum. So I guess we are going to have to find the y coordinate of b after all, because we're going to need to find the range of values between b and between a. So to find the y coordinate for b, let's plug in -2 into this function here. So let's see. F of 2 is going to be equal to -2 times, so this should be -2 divided by, I think it was -2 squared minus 5 times -2 plus 4. If we evaluate this, we're going to get -4 positive 4 minus 5 times -2 plus 10 plus 4. This is equal to 4 over 18, which is 2 over 9. Sorry, shouldn't box that. That would mean it's the answer. So our b coordinate is -2 and 2 over 9. So if we look at this again, we'll see that this range of values would permit a horizontal line that does not touch the graph of f. So the permissible values of k would be from 2/9 less than k is less than whatever was the value of the y value of the maximum, which was 2, given to us. And that will be your answer. So for the fourth function here, we're given another graph and the function of this graph. So the first part asks us to find the derivative. This should be a really simple task. So 1/3 x cubed. The 3 will move down to cancel and we'll get x squared plus 2x squared, which would be 4x, and minus 5x minus 5 would be the derivative function. And hence we have to find the x coordinate of m, which is a local maximum on our graph. So to find the local maximum, we have to find zeros of the derivative function. This is true for the local minimum too, but here, x squared plus 4x minus 5 is going to be equal to 0. Let's factor this quadratic. We need two numbers that multiply to -5 but add up to 4. So let's see. -5, so it'll probably be +5 and -1. So we'll have x plus 5 and x minus 1, and those are not our solutions because we need to find the ones that make these equal to 0. So x is going to be equal to -5 and +1. So which one's going to be our local maximum? Well, clearly on the graph, it's the one on the far left. So it's going to be the negative value. The coordinate is -5. So next they tell you to find the x coordinate of n, which is the point of inflection for this graph. So while you could take the second derivative, and it's probably a pretty good idea too, we just found the points of the local maximum, and this one's going to be the local minimum, right? Let's call this point O. The point of inflection on simple graphs like these, where the power of it's just x to the power of some number, the point of inflection is always going to be perfectly in between these 2 points. Just makes sense, right? There's the certain point where the slope is perfectly aligned with between the 2 points. It's going to be between m and o in this case. So we can take the average of these 2 points. We'll get -5 plus 1 divided by 2 is going to be -4/2, right? So the answer is -2. Is the x coordinate of n? Should be, if it looks around here. So the final part of this question asks us to find the line L, which is tangent to the curve at coordinates 3, 12. And it has to be in the form y equals mx plus b. So what can we do to get these variables? In y equals mx plus b, the m is the slope and b is a y-intercept we can solve for later. But for now, the m is going to be equal to the slope at this point because it's a tangent line. So we'll have to find f prime of 3 since that's our x value. And our derivative function was x squared plus 4x minus 5. So this will be 3 squared minus 4 times 3 plus 5. 3 squared is 9 minus 12 plus 5. Some rough mental math here. We're going to get 2. Should be right. 14 minus 12, 2. So that's going to be our slope. We'll get that y is equal to 2 times x plus b. But what can we do? Instead of solving for the b with the points we have on this graph, let's just instead use point slope form. Y minus y1 is equal to m times x minus x1. Since we have our slope here, let's plug in a point that we have, and a point that we know we must have is going to be 3 and 12 because they should be common between the function and the tangent line if it's a tangent line at all, right? It should be touching at this point and only this point. So minus 12 is equal to our slope, which is 2 times x minus 3. So let's simplify this out a bit. Y minus 12 is going to be equal to 2x minus 6. We have to add 12 to both sides. Y is going to be 2x plus 6. And that should be your answer for the tangent line. So the fifth question here, we're given a semicircle and we have an inscribed angle within, and this is a triangle. So we're given a semicircle, with center O and a radius of 5 centimeters as shown in the diagram below. Alpha is an angle measured in radians with, and here's the range, the domain, I guess, because this is our independent variable for this optimization question later. So obviously alpha can only range from 0 to 180 degrees or pi. We're going to be working in radians now because our domain is given in radians. So we're told to find the area of the triangle in terms of the angle alpha. So we're going to be using a formula, 1/2 AB times sine C. You could probably definitely do this with splitting the triangle up using right angle trigonometry. It doesn't really matter. So I'm going to call this triangle. I like to use these little indicators so I don't mess up when I'm calculating area for geometry problems, and I'm going to call these shaded areas like such. That's going to be the shaded area. So this is my nomenclature for this little question here. So obviously the area of this whole triangle is going to be the area of these two triangles added up, right? So what we're going to need is some lengths in order to use this, because we are going to need the angle and then the two sides that are connected to the angle. So in this case, it'd be 5 centimeters, and this line here, which is also going to be 5 centimeters, because obviously here's the center, and the radius here is going to be the same as the radius here. And that means this line here would be 5 centimeters. But what is this angle here? So this is going to be pi minus alpha. Is going to be our angle here, because it is 180 degrees subtracted by this angle here to make the other triangle. So the area of this triangle is going to be 1/2 times AB, 5 times 5, 5 squared, times sine of alpha, right? And this triangle here is going to be 1/2, same thing, times sine of pi minus alpha. And the total area, which I'll draw like this, I guess, is going to be equal to these two added up. So we'll get 1/2 5 squared times sine alpha plus 1/2 5 squared times sine pi minus alpha. And straight away, I'm going to notice something. If we go back to the unit circle, if you remember A, S, T, C for the positive values, pi minus alpha would mean we're using a reference angle of alpha here. So that means we'll have a triangle here, and this is going to be alpha. But the angle from the start is going to be pi minus alpha. And obviously this angle here would represent alpha here. Since we know that it's going to be an acute angle, alpha will be at least. And the obtuse angle here, it's going to range like this. Or sorry, it won't be an acute angle, but it won't exceed pi, which means this makes perfect sense. And actually, what we can infer from this is that this angle is pi minus alpha. And if you do the calculations of opposite divided by hypotenuse, we'll notice that these two are actually the same. So alpha and pi minus alpha are the same. And it also makes sense if you look at the graph. If you subtract by pi, you will get the same value as the value you plug in. So let's rewrite this. We now know with this new info that alpha and pi minus alpha are the same. Sine of alpha. Worst alpha I've ever written. But yeah. So we have two of the same term. And we have 1/2 of this one and 1/2 of this one. That just makes one of that thing. So we'll get 5 squared, which is 25, times sine alpha. And that is going to be the area of this larger inscribed triangle. So now we're going to have to start using this area. Hence, find the shaded area in terms of alpha. So my little symbol for this is going to be like this. This is the shaded area. So this shaded area is going to be equal to the entire semicircle minus that triangle we just found, right? And we know that this is 25 sine alpha. And that the semicircle is going to be half of a circle. The area of a circle is pi r squared. Pi r squared over 2 minus 25 sine alpha is going to be the area in terms of alpha. So let's write that nicely. Pi r squared over 2 minus 25 sine alpha. We can write 25 sine alpha as 50 over 2. 50 sine alpha over 2. So we can put them on the same denominator. We'll get pi. Oh, sorry, by the way. R is 5. So we know r squared is 25. 25 pi minus 50 sine alpha divided by 2. And you can do some factoring. You pull out the 25 if you want. And finally, the hard part of this question, we're going to have to find the minimum and maximum values of the area A, which is this yellow shaded area, and the values of alpha where they occur. So we're going to have a function of alpha is going to be equal somehow to area. That means when we're taking the derivative, we're going to have dA over d alpha. But first, let's write out the function. Our function of alpha is going to be this. This is our area formula, right? Because we're looking for the shaded formula, the shaded value. So I'm going to write this, also factoring out the 25 and the 2. So I'll get 25 over 2 multiplying pi minus 2 sine alpha. Of course, I did this because I'm going to be setting this equal to 0 after I derive it. So the derivative of this is the same as the derivative of this part multiplied by 25 over 2 afterwards. So let's find that. So pi is going to go to 0 minus 2 cosine alpha. And this is our derivative. And then we're going to have to set it equal to 0, which is going to be equal to 25 over 2, 0. Well, we're not going to have to write that. 2 times cosine alpha is equal to 0 to find the minimum and maximum values of alpha, of the area, where they occur for alpha. So let's divide both sides by this fraction. Does it matter? We have negative 2 cosine alpha is equal to 0. We can divide both sides by negative 2. So we're going to get cosine alpha is equal to 0. Remember, alpha is within the range 0 lesser than or equal to alpha lesser than or equal to pi. So we're going to need to use the unit circle and find the values where cosine of alpha is equal to 0. So if you remember the unit circle, we have opposite of the angle, adjacent, and hypotenuse. So cosine is adjacent over hypotenuse, so it'll be the value where the adjacent is nothing. So it's going to be on this flat line. And if you think about it, from 0 to pi, the only value where this occurs is right here at pi over 2. So cosine of alpha is equal to 0. That means alpha is equal to pi over 2. But wait, that doesn't make sense because it's asking us to find the values for the minimum and the maximum, but we only got one value and we don't know which value this is. So something we're missing is we have to check the endpoints. So I actually missed this on my test. I missed one of these solutions. I used logic to figure out that as the angle grows bigger, it should make sense, or as the angle grows smaller, it should make sense that the shaded area is maximized because this point R will move as low down as possible. And this entire triangle would be shut down to nothing because you're pulling this entire line down. And the entire area would be shaded. But I missed the other value, which was to actually have alpha go this way over to pi and fill in the entire shaded area. So if you want to use that reasoning, you could immediately write the answers 0 and pi are your maximum, but let's show this with the by checking the endpoints. So what we're going to need to do is determine whether this is a minimum or maximum by comparing it to the endpoints, by plugging in the endpoints for the value in a second. So first, let's plug this value into our area function. So we're going to get 25 over 2 times, what was it? Negative 2 sine alpha. And alpha is pi over 2. Which is going to be equal to pi over 2. So it goes up to here. And sine here is going to be 1. Positive 1. Or sorry, this part is 1. So we're going to have negative 2 times that. So we'll get negative 50. Wait, what? Sorry. This is our area formula. No, sorry, this one is. So we're going to have pi minus. So we'll get 25 times pi minus 1, all divided by 2. This is the same as 25 pi minus 25 over 2, which is a positive value. I got a negative value earlier. That kind of confused me. But, oh, sorry, this should be negative 2. So this value should be minus 50. So now we have a baseline value, and we're going to check our endpoints by plugging in the endpoints into the same equation. So we'll get 25 over 2 pi minus 2 sine of 0, which is going to be equal to, sine of 0 is just 0. We know from the graph here. So 25 pi minus 2 times 0 is just 0. 25 pi over 2. And yes, this is larger than this value because it's being subtracted by 50 and this one isn't. So we can tell that this is 1 maximum. But let's make sure to check the other one so we don't miss it like I did. Minus 2 times sine pi. Let's look at this graph again. Sine naturally has a period of 2 pi, so pi is 0 again. So this is going to be equal to 0, and we're going to get the same answer. And both of these values are greater than this value, which means the max is equal to 25 pi over 2 for the area, which occurs at 0 and pi, and that the other value we found actually happened to be the minimum, which is 25 pi minus 50 over 2, and this occurs at alpha is equal to pi over 2. And that's the answer for this part of the question. So for this question here, we're going to have a particle moving along a straight line such that its displacement from the origin, given by this function of time, s of t, s usually stands for displacement by the way, is equal to all this. And they asked us to find the velocity formula. So that is going to be s prime of t. And I can tell you that because I know that on a graph of displacement versus time, the rate at which displacement is changed according to time would be the speed, right? If you move more units per the same amount of time, then your speed is higher, right? And that's why. So this is s prime of t. So to find this, pretty simple. It should be v of t, which is equal to s prime of t, is going to be equal to 240 plus 20t minus 10t squared, right? Yeah. And we have to find the value of t when the speed of the particle is greatest, which means we have to find the maximum of v of t. So we have to find the derivative of v of t and set it to 0. And that is just equal to the acceleration. So v prime of t is equal to the acceleration of t. And to solve for that, we're going to just derive the upper formula here. So it'll just be 20 minus 20t. And that is equal to our acceleration formula. And then we're going to set it equal to 0 to find the value of t. And since we know that the previous function was a squared function, we're only going to have one I think it should be a maximum. Yes, because it's an inverted parabola. We're going to have 1 point of maximum, kind of like this. So minus 20t is equal to 0. That means that 20 is equal to 20t, and t is equal to 1 if we divide both sides by 20. So that is the value of speed of t when the speed of the particle is greatest. We don't have to question that at all because there should only be one point on this graph of speed where there is a zero slope, so zero acceleration, which means it's the greatest at that point. And now we have to find the acceleration of the particle when its speed is equal to 0. So this is kind of tricky. We're going to go back to our formula for speed, which is velocity, which is 240. I think it's plus 20t minus 10 squared, 10t squared. Minus 10t squared. Yep. We have to find when it's equal to 0, so sure, let's let it equal 0. And now we have to factor this. I'm going to rewrite it. So it's because this is the form I'm used to. And I'm going to divide everything by negative 10. T squared minus 2t minus 24 is equal to 0. We need two numbers that multiply to negative 24 but add to 2, negative 2. And I'm thinking negative 6 and positive 4. So this is going to be t minus 6, t plus 4. Let's check that. Yeah, equals 0. So t is going to be equal to negative 4 and positive 6. So that's not what they asked for, though. They asked for the acceleration of the particle when its speed is 0. So all these graphs, they actually all line up. You have your displacement graph, something like that, I guess. You have your parabola, and then you have your acceleration as the derivatives move on. But all the time values will correspond. So we just have to plug this value into the acceleration formula, which is 20 minus 20t. So we're going to have 20 minus 20 times negative 4, which is going to be equal to plus 80. So this is 100. And the other one is 20 minus 20 times 6, which is equal to 20 times 6, 120. 20 minus 120 is negative 100, I think. And this should be our answer for the two accelerations. Okay, and now for my least favorite question, because I got stuff wrong on this one. Let f prime of x be the derivative of some function f of x. The following diagram shows part of the graph of f prime of x. And it looks like an upside down parabola, which kind of indicates to us that the original function looked maybe something like this, a cubic function, but inverted because it's an upside down one, so it's negative as well. So the zeros of f prime of x are at x equals negative 1, it's going to be this one, and x equals 3, so these are zeros. And f prime of x has a local maximum at 2, 5. So remember, this is f prime of x, not f of x, right? So we have to be wary when we're answering these questions that we don't answer thinking about the wrong function. So it asks us to find the x-coordinates of any stationary points and classify them as maximum, minimum, or an inflection. So we have a maximum, but remember this is f prime of x, so this does not correlate to what we're experiencing in the real function. These zeros of the function should be stationary points. If you remember like this, these should be stationary points of the function. So the x-coordinate at negative 1, I'm pretty sure that's going to be a minimum, because you can tell it increases to a certain point. The slope is negative, which means it's going downward, which it is here. Then it finally hits 0 slope. Then it starts increasing positively, which means that there was a dip like this, right? So this is going to be a minimum. So when we have x is equal to 3, this one is going to be a maximum for the opposite reason. And also, now we're going to have to find the stationary point, which is at the maximum of this parabola, since we're going to have a point right in between the two zeros, as I mentioned earlier, that where the slope is perfectly changing between these two. So we'll get that x when it's at 2. It is a inflection. So the next part of the question, I didn't write it down, but they said find the x coordinates of any inflections. And, well, we just marked down one of the inflections. So the x coordinate is going to be 2. And the final part of the question, given that f of 0 is equal to 0, sketch the graph of function f. So we're given this, right? So some of the points to notice are going to be here, here, and here. And now that we have f of 0 should be equal to 0, that means when x equals 0, y equals 0, right? That means we start at the origin point. We know that we need to have a local minimum and a local maximum. So to sketch this graph, it's probably going to look something like this. And we have to indicate for the examiner that we have a minimum at -1, a maximum at 3, and this is a stationary inflection point at 2. And that should be a sketch of the function. So that's the end of the summative review. Thank you for watching.